Spitzer Race JPL Comforce check.
Coming, Spitzer loud and clear.
And I read you the same, and you have 6-3.
This is NASA's Spitzer Space Telescope, sister mission to Hubble, and a key tool for the study of exoplanets. You are seeing Spitzer at its actual height of 4 meters, or 13 feet, much as it appeared after its launch in late 2003. As we follow Spitzer in its orbit around the Sun, we see the Sun drift across the background stars. The floating window near Spitzer shows the calendar date of the simulation. Since Spitzer takes about 8 more days to go around the Sun than the Earth does, we will fall farther and farther away from our homeworld as it dwindles to a distant blue dot. Looking around, you see the sky as it appears to our eyes in visible light. But Spitzer's eye reveals the wonders of the infrared universe. Shifting our view to infrared light, the dark ribbons of dust that run through the Milky Way become ever more transparent. This lets us see through them to the vast populations of stars that fill our galaxy, to its center and beyond. Pushing to even longer wavelengths in the infrared spectrum, the dark clouds of dust themselves begin to glow. We see intricate structures, rich with dust and gas, filling the spaces between stars, while many of the brightest areas glow in the warmth of newly forming stars. This is the infrared universe that Spitzer shows us. An array of solar panels mounted on a heat shield provide power to Spitzer. The telescope can generally tilt 10 degrees towards the Sun and 30 degrees away from it. But within those limits, it can pivot in any direction. This allows Spitzer to point at targets anywhere within this 40-degree wide band of sky. As Spitzer tracks the Sun during its orbit, this band sweeps across the sky, giving access to any location at least every 6 months or so. 2 regions, directly above and below us, are continuously available for study all year long. This Earth-trailing orbit grants efficiencies not available to telescopes on the ground or even in near-Earth orbit. Spitzer works around the clock, collecting data on targets selected by astronomers. It only pauses to aim its radio dish towards Earth for scheduled communication breaks. This is when it sends us its accumulated data and receives new lists of targets. In May of 2009, Spitzer depleted its supply of liquid helium, used to chill its instruments to near absolute zero. Telescope temperatures then increased by about 20 degrees Celsius, still cold by most standards, but to astronomers, it marked the beginning of Spitzer's warm mission. While Spitzer could no longer see dust glowing at the longest wavelengths of infrared light, it maintained its ability to measure infrared starlight with great accuracy. This, along with transmitted software updates to improve precision, enabled Spitzer to collect high-quality exoplanet data. In fact, Spitzer's data contributing to the discovery of 7 Earth-sized planets in the TRAPPIST-1 system were collected at the start of the Spitzer Beyond phase of its mission in October of 2016. Until Spitzer concludes operations on January 30th of 2020, it will continue to help astronomers study the properties of exoplanets of all types, including ones discovered by TESS, NASA's most recent planet-finding mission.